In order to describe motion of an object in two dimensions, a plane, or three dimensions, space, we need to use vectors to describe displacement, velocity, and acceleration. Scalars and vectors. In physics, we can classify quantities as scalars or vectors. Basically, the difference is that a direction is associated with a vector but not with a scalar. A scalar quantity is a quantity with magnitude only. It is specified completely by a single number, along with a proper unit. Examples are the distance between 2 points, mass of an object, the temperature of a body, and the time at which a certain event happened. The rules for combining scalars are the rules of ordinary algebra. Scalars can be added, subtracted, multiplied, and divided just as the ordinary numbers. For example, if the length and breadth of a rectangle are 1.0 meters and 0.5 meters respectively, then its perimeter is the sum of the lengths of the four sides, 1.0 meter plus 0.5 meters plus 1.0 meter plus 0.5 meter, which totals to 3.0 meters. The length of each side is a scalar, and the perimeter is also a scalar. Take another example. The maximum and minimum temperatures on a particular day are 35.6 degrees Celsius and 24.2 degrees Celsius respectively. Then, the difference between the two temperatures is 11.4 degrees Celsius. Similarly, if a uniform solid cube of aluminium of side 10 cm has a mass of 2.7 kg, then its volume is 10 to the power of -3 meter cube, which is a scalar, and its density is 2.7 multiplied by 10 to the power of 3 kg meter to the power of -3, which is a scalar. A vector quantity is a quantity that has both a magnitude and a direction and obeys the triangle law of addition, or equivalently, the parallelogram law of addition. So, a vector is specified by giving its magnitude by a number and its direction. Some physical quantities that are represented by vectors are displacement, velocity, acceleration, and force. To represent a vector, we use a boldface type in this book. Thus, a velocity vector can be represented by a symbol v. Since boldface is difficult to produce when written by hand, a vector is often represented by an arrow placed over a letter. The magnitude of vector is often called its absolute value. Position and displacement vectors. To describe the position of an object moving in a plane, we need to choose a convenient point, say O as origin. Let P and P hash be the positions of the object at time t and t hash, respectively. We join O and P by a straight line. Then, OP is the position vector of the object at time t. An arrow is marked at the head of this line. It is represented by a symbol R, that is OP equals to R. Point P hash is represented by another position vector, OP hash, denoted by R hash. The length of the vector, R, represents the magnitude of the vector, and its direction is the direction in which P lies as seen from O. If the object moves from P to P hash, the vector PP hash with tail at P and tip at P hash is called the displacement vector corresponding to motion from point P at time t to point P hash at time t hash. It is important to note that displacement vector is the straight line joining the initial and final positions and does not depend on the actual path undertaken by the object between the two positions. For example, in Figure B, given the initial and final positions as P and Q, the displacement vector is the same PQ for different paths of journey, say PABCQ, PDQ, and BEFQ. Therefore, the magnitude of displacement is either less or equal to the path length of an object between 2 points. Equality of vectors. Two vectors A and B are said to be equal if, and only if, they have the same magnitude and the same direction. Figure A shows two equal vectors, A and B. We can easily check their equality. Shift B parallel to itself until its tail Q coincides with that of A. that is Q coincides with O. Then, since their tips S and P also coincide, the two vectors are said to be equal. In general, equality is indicated as A equals B. In figure B, vectors A hash and B hash have the same magnitude, but they are not equal because they have different directions. Even if we shift B hash parallel to itself so that its tail Q hash coincides with the tail O hash of a hash, the tip S hash of B hash does not coincide with the tip P hash of a hash. Multiplication of vectors by real numbers. Multiplying a vector A with a positive number lambda gives a vector whose magnitude is changed by the factor lambda, but the direction is the same as that of A. For example, if A is multiplied by 2, the resultant vector 2A is in the same direction as A and has a magnitude twice of A. Multiplying a vector A by a negative number minus lambda gives another vector whose direction is opposite to the direction of A and whose magnitude is lambda times A. Multiplying a given vector A by negative numbers, say -1 and -1.5, gives vectors as shown in the figure. The factor lambda, by which a vector A is multiplied, could be a scalar having its own physical dimension. Then, the dimension of lambda A is the product of the dimensions of lambda and A. For example, if we multiply a constant velocity vector by duration of time, we get a displacement vector. Addition and subtraction of vectors, graphical method. Vectors, by definition, obey the triangle law or, equivalently, the parallelogram law of addition. Let us consider two vectors A and B that lie in a plane as shown in figure A. The lengths of the line segments representing these vectors are proportional to the magnitude of the vectors. To find the sum A plus B, we place vector B so that its tail is at the head of the vector A, as in figure B. Then, we join the tail of A to the head of B. This line OQ represents a vector R, that is, the sum of the vectors A and B. Since, in this procedure of vector addition, vectors are arranged head to tail, this graphical method is called the head-to-tail method. The two vectors and their resultant form three sides of a triangle. So this method is also known as triangle method of vector addition. If we find a resultant of B plus A, as in figure C, the same vector R is obtained. Thus, vector addition is commutative, that is, A plus B equals to B plus A. What is the result of adding two equal and opposite vectors? Consider two vectors A and minus A. Their sum is a plus minus A. Since the magnitudes of the two vectors are the same, but the directions are opposite, the resultant vector has zero magnitude and is represented by 0, called a null vector or a zero vector. A minus A equals to 0. Since the magnitude of a null vector is 0, its direction cannot be specified. The null vector also results when we multiply a vector A by the number 0. The main properties of 0 are A plus 0 equals to A, lambda multiplied by 0 equals to 0, and 0 multiplied by A equals to 0. What is the physical meaning of a zero vector? Consider the position and displacement vectors in a plane as shown in the figure A. Now suppose that an object which is at P at time t moves to P hash and then comes back to P. Then what is its displacement? Since the initial and final positions coincide, the displacement is a null vector. Subtraction of vectors can be defined in terms of addition of vectors. We define the difference of two vectors A and B as the sum of two vectors A and minus B equals to a minus B, which equals to A plus minus B, is shown in the figure. The vector minus B is added to vector A to get R2 equals to a minus B. The vector R1 equals to a plus B is also shown in the same figure for comparison. We can also use the parallelogram method to find the sum of two vectors. Suppose we have two vectors A and B. To add these vectors, we bring their tails to a common origin O as shown in the figure. Then we draw a line from the head of a parallel to B and another line from the head of B parallel to A to complete a parallelogram OQSB. Now we join the point of the intersection of these two lines to the origin O. The resultant vector R is directed from the common origin O along the diagonal OS of the parallelogram. In this figure, the triangle law is used to obtain the resultant of A and B, and we see that the two methods yield the same result. Thus, the two methods are equivalent. Resolution of vectors. Let A and B be any two non-zero vectors in a plane with different directions, and let it be another vector in the same plane, as shown in the figure. It can be expressed as a sum of two vectors, one obtained by multiplying A by a real number, and the other obtained by multiplying B by another real number. To see this, let O and P be the tail and head of the vector A. Then, through O, draw a straight line parallel to A, and through P, a straight line parallel to B. Let them intersect at Q. Then, we have A equals OP equals OQ plus QP. But since OQ is parallel to A and QP is parallel to B, we can write OQ equals lambda A and QP equals mu B, where lambda and mu are real numbers. Therefore, A equals lambda A plus mu B. We say that A has been resolved into two component vectors lambda A and mu B along A and B respectively. Using this method, one can resolve a given vector into two component vectors along a set of two vectors. All the three lie in the same plane. It is convenient to resolve a general vector along the axis of a rectangular coordinate system using vectors of unit magnitude. These are called unit vectors. A unit vector is a vector of unit magnitude and points in a particular direction. Unit vector has no dimension in unit. It is used to specify a direction only. Unit vectors along the x, y, and z axes of a rectangular coordinate system are denoted by I cap, j cap, and k cap. These unit vectors are perpendicular to each other, as shown in the figure. If we multiply a unit vector, say n, by a scalar, the result is a vector lambda equals to lambda and cap. In general, a vector A can be written as A equals to modulus and multiplied by n cap, where n cap is a unit vector along A. A component of a vector can be positive, negative, or zero, depending on the value of theta. Now, we have two ways to specify a vector A in a plane. It can be specified by 1. Its magnitude A and the direction theta it makes with the x-axis, or 2. Its components to x and to y. So far, we have considered a vector lying in an xy plane. The same procedure can be used to resolve a general vector A into three components along x, y, and z axes in 3 dimensions. Vector addition through the analytical method. Although the graphical method of adding vectors helps us in visualizing the vectors and the resultant vector, is sometimes tedious and has limited accuracy. It is much easier to add vectors by combining their respective components. Since vectors obey the commutative and associative laws, we can arrange and regroup the vectors, and thus, each component of the resultant vector is the sum of the corresponding components. This method can be extended to addition and subtraction of any number of vectors. Position vector and displacement. The position vector are of a particle P located in a plane with reference to the origin of an xy reference frame is given by R equals to xi cap, yj cap, where x and y are components of R along x and y axes, or simply they're the coordinates of the object. Suppose a particle moves along the curve shown by the thick line and is at P at time t and P hash at time t hash. Then, the displacement is delta R equals to R hash minus R and is directed from P to P hash. Velocity. The average velocity v of an object is the ratio of the displacement and the corresponding time interval. The direction of the average velocity is the same as that of delta r. The instantaneous velocity is given by the limiting value of the average velocity as the time interval approaches zero. The meaning of the limiting process can be easily understood with the help of the figures. In these figures, the thick line represents the path of an object, which is at p at time t. P1, P2, and P3 represent the positions of the object after times delta t1, delta t2, and delta t3. Delta r1, delta r2, and delta r3 are the displacements of the object in times delta t1, delta t2, and delta t3, respectively. The direction of the average velocity v is shown in the figures for 3 decreasing values is along the tangent to the path. Therefore, the direction of velocity at any point on the path of an object is tangential to the path at that point and is in the direction of motion. Acceleration. The average acceleration of an object for a time interval delta t moving in x, y plane is the change in velocity divided by the time interval. The instantaneous acceleration is the limiting value of the average acceleration as the time interval approaches zero. By definition, the direction of average acceleration is the same as that of the change in velocity. We see that as delta t decreases, the direction of delta v changes and consequently, the direction of the acceleration changes. Finally, as the limit delta t tends to zero, the average acceleration becomes the instantaneous acceleration. Note that in one dimension, the velocity and the acceleration of an object are always along the same straight line, either in the same direction or in the opposite direction. However, for motion in 2 or 3 dimensions, velocity and acceleration vectors may have any angle between 0 degrees and 180 degrees between them. Motion in a plane with constant acceleration. Suppose that an object is moving in an x, y plane and its acceleration is constant. Over an interval of time, the average acceleration will equal this constant value. Now, let the velocity of the object be v0 at time t0 and v at time t. Then, acceleration equals to v minus v0 divided by the time difference t. Hence, the velocity v equals to v0 plus acceleration multiplied by the time taken. Over this time interval t, the average velocity is v0 plus v divided by 2. The displacement is the average velocity multiplied by the time interval. Motion in a plane 2 dimensions can be treated as 2 separate simultaneous one-dimensional motions with constant acceleration along 2 perpendicular directions. This is an important result and is useful in analyzing motion of objects in 2 dimensions. A similar result holds for motion in 3 dimensions also. The choice of perpendicular directions is convenient in many physical situations. Projectile motion, an object that is in flight after being thrown or projected, is called a projectile. Such a projectile might be a football, a cricket ball, a baseball, or any other object. The motion of a projectile may be thought of as the result of 2 separate, simultaneously occurring components of motions. One component is along a horizontal direction without any acceleration and the other along the vertical direction with constant acceleration due to the force of gravity. It was Galileo who first stated this independency of the horizontal and the vertical components of projectile motion in his dialogue on the Great World Systems, 1632. While learning projectile motion, we shall assume that the air resistance has negligible effect on the motion of the projectile. Suppose that the projectile is launched with velocity v0 that makes an angle θ0 with the x-axis as shown in the figure. After the object has been projected, The acceleration acting on it is that due to gravity, which is directed vertically downward, which can be represented as acceleration equals to minus gravity multiplied by vector j cap. The horizontal component of initial velocity is given as v0 cos theta 0, and the vertical component of initial velocity is given as v0 sine theta 0. At time t, the horizontal component of velocity at time t can be obtained as v0 cos theta 0, and the vertical component of velocity can be obtained as v0 sine theta 0 minus the acceleration due to gravity multiplied by the time t. It must be noted that one of the components of velocity, that is the x component, remains constant throughout the motion, and only the y component changes, like an object in free fall in vertical direction. Equation of path of a projectile. What is the shape of the path followed by the projectile? The path of the projectile is a parabola. Time of maximum height. How much time does the projectile take to reach the maximum height? At the maximum height, the velocity tends to zero, and hence, the time of maximum height can be obtained by the equation v0 sine theta 0 divided by the acceleration due to gravity g. The total time during which the projectile is in flight can be obtained by twice of v0 sine theta 0 divided by the acceleration due to gravity g. The maximum height reached by the projectile can be calculated by the equation v0 sine theta 0 square divided by twice the acceleration due to gravity g. The horizontal distance traveled by a projectile from its initial position to the position where it passes y equals 0 during its fall is called the horizontal range. R is the distance traveled during the time of flight. The range can be obtained using the equation v0 square sine 2 theta divided by the acceleration due to gravity g. When an object follows a circular path at a constant speed, the motion of the object is called uniform circular motion. The word uniform refers to the speed, which is uniform, constant, throughout the motion. Suppose an object is moving with uniform speed v in a circle of radius r, as shown in the figure. Since the velocity of the object is changing continuously in direction, the object undergoes acceleration. Let us find the magnitude and the direction of this acceleration. Let r and r hash be the position vectors in v, and v hash the velocities of the object when it is at point P, and P hash is shown in the figure. By definition, velocity at a point is along the tangent at that point in the direction of motion. The velocity vectors v and v hash are as shown in the figure. Change in velocity, delta v, is obtained using the triangle law of vector addition. Since the path is circular, v is perpendicular to r, and so will be v hash to r hash. Therefore, delta v is perpendicular to delta r. Since average acceleration is along delta v, the average acceleration a is perpendicular to delta r. If we place delta v on the line that bisects the angle between r and r hash, we see that it is directed towards the center of the circle. The figure shows the same quantities for smaller time interval, delta v, and hence a is again directed towards the center. In this figure, delta t tends to 0 and the average acceleration becomes the instantaneous acceleration. It is directed towards the center star. Thus, we find that the acceleration of an object in uniform circular motion is always directed towards the center of the circle. The average acceleration becomes the instantaneous acceleration when the time difference delta t tends to 0. It is directed towards the center. Let's now find the magnitude of the acceleration. The magnitude of acceleration is, by definition, given by a modulus equals to limit t tends to 0, delta v divided by delta t. Let the angle between position vectors r and r hash be delta theta. Since the velocity vectors v and v hash are always perpendicular to the position vectors, the angle between them is also delta theta. Therefore, the triangle CPP hash formed by the position vectors and the triangle GHI formed by the velocity vectors v hash and delta v are similar. Therefore, the ratio of the base length to side length for one of the triangles is equal to that of the other triangle. Thus, the acceleration of an object moving with speed v in a circle of radius r has a magnitude v squared divided by r and is always directed towards the center. This is why this acceleration is called centripetal acceleration, a term proposed by Newton. A thorough analysis of centripetal acceleration was first published in 1673 by the Dutch scientist Christian Huygens, but it was probably known to Newton also some years earlier. Centripetal comes from a Greek term which means center-seeking. Since v and r are constant, the magnitude of the centripetal acceleration is also constant. However, the direction changes, pointing always towards the center. Therefore, a centripetal acceleration is not a constant vector. We can also express centripetal acceleration in terms of angular speed as centripetal acceleration equals to omega squared multiplied by r, where omega is the rate of change of angular displacement. The time taken by an object to make one revolution is known as its time period t, and the number of revolutions made in 1 second is called its frequency v, which is equal to 1 divided by t. Hence, acceleration expressed in terms of frequency is 4 pi squared multiplied by the frequency v squared and the radius of the circle r.